this is what they send out in the manual, and the manual will say, oh, you need to relubricate this, or you need to replace this portion of the machine every so many hours, okay? And whether it needs it or not, it's just a schedule, and somebody's figured out that you need to replace that. And this was developed in the airplane industry.
Wow.
13, condition-based maintenance, and that's kind of what we do, okay? We measure the condition, and we only do maintenance when our measurements say something could go wrong. That, you can see, you're substantially less than just reactive maintenance. And then finally, what they call proactive maintenance. And what that means is, it's basically condition maintenance and proactive now almost always run together. And you can see that what that means is, you may say, okay, we need to change the grease we use in this bearing because obviously we haven't got quite the right greasing because it keeps wearing out. You might do something like that, or you might say we need to do a better job balancing our machines or aligning our machines when we install them. That would be proactive type maintenance, okay? Seeing ahead of time what's wrong, but still using condition-based principles. And you can see that now you've went from $17 per horsepower per year maintenance to $5 per year per horsepower. Okay, so reactive maintenance, what is it? We have a breakdown again. The building's on fire. Okay. Time to call the fire department. Okay. So this can be extremely expensive type of maintenance.
Yes.
And the real loss is not generally, sometimes it is, but generally the real loss is not the machine. The real loss is the production.
Yeah.
Yes.
Downtime.
Downtime.
Downtime. You know, I have a paper machine and I make $20,000 an hour in profit if that machine's running. But I have a $10 piece of equipment fail. Boy, that's tough because it shut my machine down for half a day, you know. And so at any rate, so there's some advantages. There's no investment in training. Don't have to worry about planning. It'll plan for you. Disadvantages, catastrophic failures, okay? Collateral equipment damage. That happened in Russia. That was a dam in Russia. The whole dam self-destructed. Unplanned outages, high and complicated repair cost. Okay, overtime cost, and the biggest, lost revenue. Okay, so preventative maintenance, that's just simply like an airplane falls apart, airplane wing falls apart every, $150,000 hours. This key part of an airplane fails on average. So let's go back and instead of every 150,000, let's just replace it when we get to 100,000 hours. That can be really safe, especially if you've got math behind it. That was started in the early 1920s. Okay. Then in that period of time, people were afraid to fly an aircraft because they tended to catastrophically fail. So they went through and stress tested all the key components, and they tested them to failure. I've been up to Boeing and seen the big machine that they put 747 wings in, and they flex, and I've seen one actually flexing, and they flex those tips up and down probably 150, no, see, is it 100 meters? No, not that much. They probably go 10, 20 meters up and down with the wings every probably 40, 50 seconds or 2 or 3 times a minute. They'll flex those wings. And what they're looking for is cracks in the structure. They calculate the standard deviation, and then they calculate mean time between failure. This is what I was an expert at when I graduated from school, by the way.
Wow.
And I used to do workup formulas. Used to work up formulas that could predict this type of stuff, failures. So, at any rate, a thing called regression analysis. I became quite the school expert in that. A replacement, maintenance, and inspection, or RIM time, was determined by decreasing the RIM time by subtracting numerous standard deviations. So you'll know from school that if you figure out the mean time between failure is, whatever, so many hours, and then you take 3 times the standard deviation and come back from that, that'll give you 95% probability that part won't fail after that amount of time, or at that amount of time. Well, you have to go back many more standard deviations, probably 8, 9, to be safe enough for an aircraft to do that, to use this strategy. The result is extremely low and measurable risk, provided enough standard deviations are used. Okay, so replace it before it breaks. It works. Okay. However, there's a downside we're going to talk about. Advantages: very low risk of interruptions to production. Cost savings: it's 28% better than breakdown maintenance. That's good. Mm-hmm. Okay. Disadvantages: high program effort compared to condition-based maintenance. You got to figure all this stuff out. Okay. Another problem: too soon. A lot of times a component can go 3 or 4 times its projected life and do it perfectly safely. Okay. So a lot of times you find you're throwing away parts that only have a low probability of failure, and if you could measure them some way, you could not have to throw away good parts.
Yeah, true.
Okay.
Yes.
Yep.
Not soon enough.
Yes, not soon enough. Okay, would be unexpected breakdowns, but the real thing is too soon. Okay, you end up stopping and throwing away a lot of perfectly good parts.
True.
Oh, maybe you can sell it in the second-hand market.
Yes, yeah,
Recon.
you could.
Yes.
Yes, in fact, they probably do. But at the same token, if you're really wanting to run in a more efficient program, that's not the way to do it.
Yeah, that's
okay.
right.
So a guy did a study, Brian Tiet, back in the late 60s, I would think, in mid-70s. And he used to work for the industrial division of Travelers Insurance Company. He did a study on steam turbine failures. 60% of all steam turbine failures happen immediately after a rebuild. Wait.
Wow.
What does that mean? Well, first
Crazy.
off, let's think. A steam turbine is a complex machine, okay? But what they're saying is, you get all these failures. There's one pitfall of preventative maintenance, is that one spends a lot of money and time repairing equipment that does not need to be repaired. As my grandpa told me, if it ain't broke,
don't fix it.
Correct.
Yes, there's a certain amount of logic, but if we did that, we would be right back to wait till it breaks.
Yes.
So that's where condition-based measurements come in. Then think about this: if you had a heart attack, okay, I'm pretty old, so I go in and I get myself checked out about every 6 months, and so far so good, But my dad was doing this, and when he was about 60 years ago. When he was 50 years old, they said you got a lot of artery blockage. and he goes, you could have a stroke or a heart attack. And my dad said, my dad doesn't even know about this stuff. But he said, so what are the odds of me having a heart attack in the next, say, 5 years? Oh, and he goes, maybe 4 or 5%.
Oof.
And he goes, well, if you go in and do open heart surgery, what are the odds of me having complications or dying? And he says, about 5 to 10%.
It's even higher.
And he goes, wait. And so he started going in more often. He changed his diet. He started working out, kind of doing long walks every day. And, he went in for the next roughly 10 years he went in, and everything looked fine and was staying the same, if not even a little bit better. And then finally it started getting worse, and they said, okay, now it's worse. And he said, so what are the odds of me having a heart attack? He goes, probably 10, 15% if I had to put a number on it. He goes, okay, time to have open heart surgery. Okay. So you can imagine that's a lot like what we're doing. If you're monitoring your condition all the time, you can change the way you're living and extend your heart's lifetime. Okay? And that's why I ski so much. I figure it's good for my heart. So we measure and evaluate machine condition. We spot machine faults before they cause breakdowns. Maintenance, repair, replace only when needed. And work to coincide with planned outages. So you go, well, I know that this isn't running as good as it could, but we can easily make it another month till we have a planned shutdown, and let's replace that bearing then. In the meantime, grease it a couple more times, than we normally would. You can order parts in advance, so you don't have to carry as much inventory of spare parts. You can arrange for needed labor and knowledge resources in advance. I knew I was friends with a guy named Ken Forrester. And what Ken did, he worked for a company called St. Clair Oil, and he was the first guy ever to go into, he was their lead engineer for the entire company. He went in and said, oh, we're not going to have, how did he put it? He said, I have all these engineers, and I really only need them during shortly before and during outages. But he goes, we have them your time. So they started buying pumps, and he made the pump manufacturers. He said, look, when we have an outage, I want part of our contract to include what you're going to charge me to have an engineer in here a month beforehand to help plan the outage and actually supervise the actual repair of the pump. And so eventually they got rid of almost all of their engineers, probably 60, 70% of their engineering staff, reduced staff a lot, and they did just as well, in fact, maybe even a slight improvement, okay? And all because they had arranged for knowledge resources to be there in advance. And a really interesting strategy. So you go to Exxon refinery over in the Bay Area, and driving down the road to get to the refinery, every big pump manufacturer, you name it, they all have now offices as you're driving up. It's kind of funny, but you'll see Gould Pumps, all these different companies all now have offices there, because they were like the second company to start doing that. So we want to optimize the life and production of your machine. 48% savings over breakdown maintenance. You're old, but you're running well.
Yes.
Okay. Proactive. Measure and evaluate machine condition is most often added to a condition-based maintenance system. It seeks to identify potential root causes of machine failures, and one can then look for ways to correct potential root cause failures, thus avoiding premature equipment fail, extending the usable life of machinery, and proactive maintenance combined with condition-based maintenance is like a money machine.
Yeah, money printing machine.
Yep, it becomes a source of revenue for you, really. So corrective actions may include changing your process. I've told people you need to slow down your paper machine. I said, not a lot. Slow it down 4 or 5%, but I don't think you'll have as many outages. And they didn't, because the machine vibrated a lot less if they slowed it 5%.
Yes.
Re-engineering, and the ultimate thing was, by the end of the year, they had produced more, okay, by running slower, but they could run more continuously. Re-engineering a part or an installation, changing routine schedules such as lubrication. what we find with a study was done over at SKF while we worked there. Jim was there too at that time. And this guy came up with a study, was from over in Germany. And Andre said, did this huge study, and he said, I think he said 45% of all rolling element bearings are due to over lubrication. And that was like a shock, you know. But but you pump too much grease in the bearing, then there's no air in the bearing, and so the grease gets pushed in a circle, roughly the running speed of the machine, and it gets hot because there's no air in there at all. It gets hot, and then the grease or the oil, the lubricant, runs out of the grease or runs out of what they call the soap. And the oil runs out, and you have this white gunky stuff left in the bearings. And it's interesting. Hey, slowing down or speeding up a process. That paper machine, they could have actually found a speed possibly even faster that they could have ran, where the whole machine, nothing would be in resonance. The whole machine would run smoother. They could have just as easily done that. All relative process parameters should be monitored and trended. So your production per hour, the materials you use in production, the temperatures you're using, feed rates, everything. If you can monitor all this, a lot of times they will correlate to high vibration. Temperature, pressure, oil condition, feed rates, all of that. So summary, this is just basically showing you what that chart showed you initially. You know, it doesn't take a rocket scientist to figure this out. Okay. And I don't know, and this is another way to look at the same thing, and then I'll let you guys go.
Operative capacity over time.
Over time, okay? And I kind of came up with this idea of operative capacity over time, calling it that. And it's the number of widgets produced over time, okay? And then unit production over the lifetime of a machine. So you graph the two against each other. And if you look at, just take a linear curve here, and you look at this, the area underneath equals the potential operative capacity of a machine over its lifetime. So that area will represent that production, we'll say. So the ideal maximized operative capacity of a machine is how many widgets it can make during its lifetime with the following caveats. Optimize widget cost over the life of the machine. Optimal capacity is reached by preemptive maintenance measures that assure product quality with a low risk of production failure. And so involved in that is cost, okay? So here's your reactive maintenance, okay? That's what you're going to get out of your machine. If you go to preventative maintenance, you're going to get this much more out of your machine. If you go to condition-based maintenance, you're going to get even more. And finally, if you automate your condition-based maintenance, and we have devices that do that measure vibration. Shoot, I had it right here and I don't see it. We have these little units. I'm not sure where it's at. You have these little units that you can see that actually hook up, and you hardwire accelerometers to it and temperature if you'd like, and they can measure it all the time. That's the most ideal.
I used those back then. I know those units, like those sensors.
Yeah. Yeah, I'm trying to.
That means you have a relay. You have a relay sitting somewhere in your office right now.
Do I have what?
Do you have a relay sitting in your office somewhere right now to connect all of these sensors together?
Oh, no. Well, I have a little machine over in the closet because this is my house. And so I have a little machine over in the closet we use to measure vibration. I use it, in fact, I'm using it right now to test the 9043 remote monitoring box and see if we can balance with it and stuff. We're having some promising results. I'll show you. Almost done with this. So you can run through this on your own, but then if you add, okay, proactive, that actually increases the whole life of during the whole life of the machine. It actually expands its capability. Okay. The other way to think of this, and I like this one the best, is failure risk in the bathtub curve. When you first start a machine, hang on, let me get my laser pointer going here again. Maybe. Oh, don't have it now. No, if it's a magnifier, here we go. There we go. Laser pointer. So at the first part of this, when you first install a machine, you know, back to that Brian Tiet thing on those turbines, a lot of times you have a high exposure of failure because you're just starting a machine up and maybe you didn't install it correct. Once you get it all fixed, then it kind of goes along, and along's a long time. So your risk of failure is high initially, but once you get this thing in and make it's all running right, your risk of failure stays fairly low for a long time. That becomes the useful life of the equipment. Then it starts to wear out, and the risk of failure starts to go back up. So this is what we call a bathtub curve. Okay, that's breakdown maintenance right there. In this area, we're just going to wait till it breaks, okay, and then fix it. If you go now, and we go into preventative maintenance, okay, so we're in there fixing things, even if it doesn't need to be fixed, we're just going to replace something. We're going to replace those bearings every 50,000 hours, okay? And now so that reduces the risk of failure, and it extends the life of the projected life of the machine. So now we go on, and we add in here condition-based maintenance. Now, we still run high risk when we first start up a machine, but now you have a much reduced risk of failure, okay? And you've extended both the wear out time and the mean time between failure out further to the right, okay? That's a data collector with spectrum and time waveform capability, software for trending, all right? And then finally, if you add proactive maintenance, that means you've done things, condition-based maintenance, and now you've added continuous protection.
This is with this product, I think, with the sensor connect to respective possible vibration point.
Yeah, and these are the boxes. These 9034 and stuff. These in 9038. They have an 8-channel one. These are the type of boxes to use, and they're super easy to hook up. And you can actually tie these things into like your process control on a machine.
Yes.
You know, yeah, we can give you outputs for this that they can take in, and then they can say, oh yeah, look at this, it's going to fail. We're getting a warning alarm, and it's right in there. Okay, residual risk decreases. Useful life increases. Here's another kind of graph. This is your investment costs, okay, over time. Breakdown. You can see here that over time.
Wow, interesting.
These may be pretty expensive to buy, but over time it reduces your overall cost. It reduces your risk of failure. And I think when you present this, especially to more management types, this makes sense to them. Oh, you mean if we buy this machine, yeah, it's going to be more expensive than buying one of these, but over time it pays for itself because it's looking at a machine 24/7,
Yes.
all the time. If it's running, it's watching. Now, an important thing, and I mention this in all of my presentations, there's always some residual risk. Always. You can't, nothing's perfect. What are typical? Ignoring condition monitoring systems, you know. Boeing telling me that there's something wrong with the monitor, not their machine, you know. I went in, I said, there's nothing wrong with it. And they go, it's working fine. You got a problem, and here's what your problem. I even told them what the problem was. Oh, it can't be that. and stuff. And then the first time they called me, it was a bad bearing. And I said, it is. My machine doesn't lie. We haven't trained it to do that. It just does not know how to lie. It just simply tells you what it's doing. And it's doing that. Oh, you made this machine. You designed it yourself. You used the wrong bearing. In that bearing, in that application, the bearing won't last for more than about 24 hours. And he figured it out using the L10 life formula. They actually said, "Oh, you guys are BSing." I said, "No way, no way." They'd only ran it about 6 hours, okay? And so they continued to fire it up. The maintenance guy called me up like 2 days later and goes, "You're not going to believe this." I go, "What?" He goes, "At 23 hours, the bearing failed." And I go, "Well, that was a pretty good prediction." He mentioned 24. But there's always residual risk. I did some work for Ford Motor Company, okay? And they have this carousel. They have diesel engines, and they come in one side, and they hook them up, and they start them up, and they run through these cycles. It literally is like a circular carousel. And these motors are each in their own little bay, and the bays rotate around. When they get to the other side, the guy disconnects them. Well, all around the top is a hood with about a 20 centimeter or 20 millimeter crack opening that goes around the whole rim of this big circle, whole thing, and that's and it's connected to a fan on the roof of the building, and any exhaust gases that happen to leak get sucked out. Some guy, I did not plan this. Some guy had a shop towel like this, literally just like this, and he held it up and let it go, and it sucked up into the fan. And this fan was really kind of a cool fan. It was real high speed, belt-driven fan, but really at a high RPM of something like 9,000 RPM. And then the blades in the fan were literally airfoil shaped, like an airplane airfoil, and they were made out of sheet metal. So they wasn't single surface, they were dual surface. So this thing ran and sucked the air out. And when this rag hit that fan, it broke, the blades smashed because they were made out of sheet metal. And it shut Ford Motor Company down for 2 full days.
2 full days.
And stuff. Okay? You could have all the, and so we put a monitoring on this system on it. I said, "You have to know something." "What's that?" I said, "This would not prevent that failure. The only thing this would have done is reduce the damage, because it would have shut off the instant it started. Within a couple of seconds, your system would have shut the fan down." So I said, "But you still, so you always have residual risk. Human error, catastrophic event, earthquakes, floods, hurricanes, all sorts of things." So why vibration measurement? Vibration measurement really is almost the keystone of any condition-based maintenance technology. Everything relies on this. Temperature happens after vibration increases. Vibration is your primary measurement to see how smoothly your machine runs. There's also contributing technologies, vibration. You can have thermography for temperature. Of course, it follows vibration typically. Oil analysis is important. Other type of technologies, electric motor testing, ultrasound measurements. We have a really cool ultrasound, and it's the first ultrasound machine I've seen in over 30, 40 years. But I don't know if you guys can sell it over there, because we do buy the guts of this thing from China. But this thing here has an ultrasonic microphone. And so when you look at a machine, if it's got a bearing rub or anything, that part of the machine will light up, picture. It's kind of cool. But it still does not replace the reliability in that trend graph that you can build by measuring those same high frequencies with an accelerometer. So, yeah. And then finally, I kind of drew this up, just a little bit of a, typically what happens, you have a machine that's in your kind of asset pool, you've got route-based measurement checks, the machine alarm, machine and alarm, you analyze, yeah. Does the asset require corrective action? No. Then it goes back into you put it back into the thought pool, okay? Yes. You issue a work order, you perform the corrective maintenance, and now it goes back into the machine asset pool. So just kind of a quick little thing. So understanding vibration technology, there's kind of a process you go through: detection, analysis, something that people do way too much. They spend a lot of money in analysis, and they really don't need to, because you're going to have to replace the bearing. I don't care if it's the inner or outer race. And then correction, verification, monitoring metrics. What should you monitor? And then here's just some of the other justifications: high production risk, loss risk, high asset replacement cost, high asset repair cost, unexpected asset failures, a lot of those, low asset availability. So you want to have this machine available to make things, insurance premiums. So yeah, back to the beginning. So I will, let's see if I can get out of this now. Here we go, click.